Alright, so in this video I'm gonna be explaining another important paper with the title Walking Out of the WL Hierarchy, Graph Learning Beyond Message Passing. This paper in 2023, they propose a CRAWL, a novel neural network architecture for graph learning. Like graph neural networks, the layers of it update node features on graph and thus can freely be combined or interleaved with GNN layers. Yet it operates fundamentally different from message-passing graph neural networks. Its layers extract and aggregate information on subgraphs appearing along random walks through a graph using 1D convolutions. Thereby, it detects long-range interactions and computes non-local features. As the theoretical basis of our approach, we prove a theorem stating that the expressiveness of it is incomparable with that of the WL algorithm, and hence with graph neural networks. That is, there are functions expressible but not by GNNs and vice versa. This result extends to higher levels of WL hierarchy and thus to high-order GNNs. So Kroll processes random walks with convolutional neural networks to extract information about local and global graph structure. We initially sample a large set of relatively long random walks. For each walk, we construct a sequential feature representation which encodes the structure of all contiguous walk segments up to a predetermined size. And these features are well suited for processing with a 1D CNN, which maps each walklet to an embedding. These walklets embeddings are then used to update latent node states. By repeating this process, we allow long-range information about the graph structure to flow along each random walk. So this is an example of information flowing Kroll layer for a graph with 8 nodes. We sample a walk and compute the feature matrix based on node embeddings F, edge embeddings G, and a window size of S equal to 4. So to this matrix, we apply 1D CNN with receptive field R equal to 5 and pull the output into the nodes to update their embeddings. We call contiguous segments of a walklets. We call them walklets. The center of a walklet of even length is the node WI plus GJ divided by 2. For each walklet, we denote by G of W the subgraph induced by G on the set. For a walk W and a local window size S, we construct the matrix representation that encodes the structure of all walklets of size S plus 1 in W, as well as the node and edge features occurring along the walk. Given a walk of length L minus 1, in a graph G, a d-dimensional node embeddings, a d-prime dimensional edge embeddings, and a local window, we define walk feature matrix X. So the first dimension of each of these matrices is indexed from 0 to L minus 1. Now node feature sequence F sub W and the edge feature sequence G sub W are defined here. And we define the local identity relation and the local adjacency relation. Now the matrices are binary matrices that contain one row for every node in the walk. The bit string for V sub I encodes which of the S predecessors of V sub I are in W are identical to V sub I. And for any walklets, the restriction of the walk feature matrix to rows contains a full description of induced subgraph. And this stack of walk feature matrices can be processed in parallel by CNN. So a crawl network iteratively updates latent embeddings for each node. The teeth layer constructs the walk feature tensor using h sub t-1 as its input node embedding. And the graph edge feature, this is graph edge feature. The walk feature tensor is then processed by a convolutional network. So this is the top one is the update procedure of latent node embeddings. Omega is a set of random walks, and the bottom layer is just stacking all of them into layers. So it's just 3 layers of crawl network. Then we give it to global pooling, MLP, and then. So the output is a tensor. The output of this convolutional neural network here, C, is a tensor. The second dimension is L-1 instead of L, as no padding is used in the convolutions. So it is the embedding computed by CNNs for the walklets. Since crawl layers are based on iteratively updating latent node embeddings, they're fully compatible with conventional message passings. So the additional strengths of crawl has 2 different routes. Crawl detects small subgraphs, whereas GNNs cannot even detect triangles. Crawl detects long-range interactions, whereas GNNs are local with a locality radius determined by the number of layers. And they did it for different data sets, MNIST, CFAR10, and you see the crawl has a good performance. Also, they did on these data sets, these are good for long-range graphs. And they did an ablation study. Node features, edge features, adjacency, identity encoding, walk strategy, no backtrack is NB. This is no backtrack. And if your strategy is uniform, we call it UN. So these are the data sets that they use. Peptides, these are very good for example, peptides structs has 11 classes.